today a visitor from Rutgers University in New Jersey, Professor Richard Ludescher, although he has been staying a few months at Oxford in Britain, and that gave him a nice opportunity to fly across the Irish Sea and see us here in Cork. So now we will have an interesting talk by Professor Ludescher, but let me introduce a little bit more. You have seen his abstract and CV perhaps on the communication, but I had the pleasure to learn to know Professor Ludescher exactly 30 years ago, in 1989, when I was staying my first year at Rutgers University in New Jersey, and Rich was quite newly appointed professor at that time at the university. Now, then, since that time, he has done different studies and research at Rutgers, but he has also contributed a lot to the administration in various areas, being a director of graduate programs and co-campus dean for undergraduate education, and many other administrative roles. His PhD is from University of Oregon, and he has an undergraduate background in anthropology and philosophy, so that's quite interesting contribution to food science. So please, Rick, go ahead.
Thank you. So it's a real pleasure to talk today. I'm going to be talking about a technique that's not used that often in food science, and diving into it pretty deeply. So if you come across a point where you really don't know what I'm talking about, feel free to raise your hands, because if I lose you and you spend the rest of the talk looking at your phone, that's not good. All right, so what I want to talk about is how we can use a spectroscopic technique to get at issues of food quality. And the key thing to recognize, of course, and you realize is that the chemical and physical properties of biomaterials are directly related to what we call quality in terms of the eating quality. Things like the pH, which affect taste and reactivity, viscosity, mouthfeel, but also engineering, water activity, which is of course central to microbiological safety, but has implications for texture and reactivity, the polarity of a matrix, of course, hydration, how much water it can hold, its solubility, and how things partition into it. Molecular mobility, but the ability of molecules to sort of move locally is a central characteristic of amorphous materials, and pretty much determines many of their properties. And of course, the structure affects everything. And so if we can come up with it, and we have in many, many areas, come up with very specific analytical techniques to monitor very specific physical and chemical properties, we can then get at issues of quality. And what I want to talk about is the use of fluorescence to get at these issues. And it's not done now very often. But of course, one of the things to realize is that when we're talking about use of fluorescence in foods, you may not realize that almost everything you eat is fluorescent. And that's because the plants, the fruits and the vegetables, and even some of the grains that we're making many of our foods, and certainly the proteins as well, and the meat, that go into the foods that we're composing contain naturally occurring molecules which are fluorescent. But then we're also synthesizing many molecules and putting them into food, and many of these molecules are fluorescent. So the foods that we're eating are fluorescent either naturally or because what we add to them. And fluorescence, and this is an example of some, and what I'm going to be talking about is use of fluorescence for all those with red. You'll see data from each of those, but there are many, many more. And these are the kind of molecules, you're talking about ring structures typically, more or less 1, 2, 3, or 4 larger rings with groups on them. And the key thing about fluorescent molecules and why this research can happen is that fluorescent molecules have the ability to be used as optical probes, and have been used as optical probes in chemistry, biochemistry, biophysics, and now cell biology for the better part of 50 to 75 years. The key thing is that the molecule, the fluorescent molecule, responds to its environment. because it is fluorescent, it sends out a signal which is related to the way it responds to its environment, and by understanding how the fluorescence from any individual molecule can be influenced by its environment, you have the ability to use that molecule as an optical probe, a spy of what's happening. And the kinds of probes in analytical chemistry, they're just, I mean, it's a cottage industry to synthesize novel molecules that may be sensitive because they bind to, for example, ions, or metal ions in particular, found in the environment or elsewhere. And so we have many cases of probes being used to monitor pH and polarity and oxygen concentration, viscosity, mobility, membrane potential, concentration of ions, et cetera. So what we'll be using is there are various sort of properties of luminescence, and by I use the word luminescence because I'll be talking about both fluorescent and also phosphorescent molecules. So the fundamental sort of property to talk about is what kind of emission is it? Is it prompt emission, i.e. is this emission that's occurring from initially excited state, a fluorescent state, a singlet state, and the emission is occurring on a nanosecond time scale, so we call that prompt emission, and that's fluorescence from a singlet excited state. But then there's also delayed emission, and that delay can be a microsecond to as long as tens of seconds, and that's usually due to a triplet state, so there's interconversion from a singlet to a triplet state, and the triplet state is long-lived, and then you end up with emission occurring on lifetimes out to seconds. And then the properties of either the prompt and delayed emission is the intensity of that, how many photons come out, which is related to what's called quantum yield. So the quantum yield can be 1, i.e. every time a photon is absorbed, another photon can be emitted. And then it's also related to the lifetime of the emission is also related in a sort of complicated way. I'll go into that in more detail. And so this is related to what quenches the excited state. And it turns out that quenching is a big part of what we'll be talking about today. So molecules have different ways they interact with their environment, different ways the environment can quench the excited state. And by understanding that in each of the probes that we're dealing with, we can get information about what's happening in the local environment by seeing how the quenching is occurring. The characteristic timescales are of the order of nanoseconds for fluorescence and micro to seconds for phosphorescence. But a second major feature is how the excited state interacts with its environment, and that can influence the energy of the emission, which of course is the wavelength of the emission. Emission can occur on the ultraviolet wavelengths all the way to the infrared wavelengths. And this is sensitive to the actual emission for each molecule is governed in large part by the structure of the molecule, but the environment can influence it sometimes to a fairly extent, a large amount, and that's due to how bonding interactions happen between the molecule and its local environment. So if you have a polar excited state and a polar environment, you can stabilize the excited state and affect the emission to actually change the color of the emission. There are some molecules that the emission can shift 150 nanometers depending on the local environment, so it's obvious what kind of environment. You can literally just look at the molecule and say that's in a polar environment, that's in a non-polar environment. You say that's acetone, that's ethanol, that's water. There's another property which I'll not be talking about, but it's also a full range of possibilities, and that is by measuring the polarization of the emission. You can actually see the excited state, what kind of rotational motion is occurring in the excited state. I will not be talking about that. There's an enormous number of possibilities there as well. So to give you sort of orientation, this is sort of like an overview of what we'll be talking about. We'll be talking about 3 separate cases, kinds of molecules that we'll be using to study their interaction with the environment to tell us what they can tell us about local environment. And so to understand those, the best way to think about it is in terms of this energy level diagram. It's called the Jablonski diagram, or energy level diagram for optical emission. And what we have is a vertical axis which represents energy, and the horizontal axis doesn't represent anything, except sort of different ways the molecule can be, the different states the molecule can be. So the molecule starts out in its ground state, not vibrationally excited. It's in a ground electronic state, absorbs the photon, and and it can absorb a photon to go to the first excited, second excited, and even perhaps a higher excited. But it's absorbing a photon, maybe ultraviolet, maybe red, or maybe green, whatever its sort of local structure gives it, and it excites into what's called the singlet manifold. And in the singlet manifold, it rapidly loses energy to drop to the lowest vibrational state. These lines here are vibrations of the first singlet excited state and vibrations of the second singlet excited state. So it always relaxes. This is called Cauchy's rule. It always relaxes to the lowest vibrational state of the excited state, and then just hangs around there for a while. Now, by rapidly, I mean like in femtoseconds it gets to here, and then maybe hangs around in the state for like a nanosecond or 10 nanoseconds or so. And then it can do something from that state. It can emit a photon. It's a fluorescent molecule. It has to be able to emit a photon, or we wouldn't be talking about it. We wouldn't be studying it this way. And so, but once it's in the state, it can only do one thing. It can emit a photon or not. And so if it emits a photon or not, it changes the intensity. Because when it's not, the intensity goes down. It can couple to the ground state by a non-radiated decay. This is some sort of interaction which allows it to lose its energy in small increments and go down to the ground state. Or it can go over to another excited state. In this case, I've indicated it as a triplet manifold. But the other state could be another singlet excited state. So just keep that in mind. So basically, once it's absorbed a photon and gone down to its lowest energy level, things can happen. And basically, depending on what else can happen here, we have different classes of molecules that may interact with their environment in a different way. So I think the first one I talk about is actually the triplet manifold, if I recall. And so what we're talking about now is molecules that, because of their structure, have a high quantum yield for undergoing what's called intersystem crossing and going over to a triplet state. And what's characteristic of the triplet state is that this transition involves a spin flip. Question?
Yes, so if a photon transfers from a singlet manifold to another singlet manifold, which has another photon in it,
It won't have another photon in it.
Okay.
No, what it is, it's the molecule, it's a different state of the molecule.
Okay.
It's going to be in this excited state. It doesn't have a photon in it. What it becomes now is an excited state.
Okay.
And there are other kinds of excited states that can be.
Okay, so it's not excited states being shared by multiple photons. Okay.
No, because you can get into this excited state by something other than absorbing a photon.
Okay.
Yeah, but for example, the photons that are being emitted by these fluorescent lights,
Yeah.
the excited state of the ions is generated by electricity.
Yes.
And then in that excited state, they're emitting a photon.
Okay.
Yeah. So we're just talking about photoexcitation of these states, but these states pre-exist independent of the photons.
Okay.
They can be occupied in various ways.
Okay.
They're just different eigenvalues of the wave function which characterizes the molecule.
Okay.
But we don't want to talk about this.
Okay.
Because it gets way too complicated, way too fast. Yes?
So I was wondering about Cauchy rule that you
Yeah.
were mentioning. So we have actually the absorption bandwidth,
Yep.
and we have also the emission bandwidth.
Yep.
So at times they both overlap.
Yeah. So what happens there is that the overlap corresponds to the 0-0 transition.
Okay.
The overlap is because this energy is the same going up and going down.
Okay.
So in some molecules, there's that don't interact strongly with their environment, you get a lot of overlap, and the 0-0 overlaps.
Okay. But they overlap bit a lot. Now my next question is actually, so Cauchy rule also says like the quantum yield will be same. Means when it says everything decays to
where do you expect the same one?
So what's my question now is like, if we excite below a absorption band, below a emission bandwidth, so you have the emission band, if I excite at the emission, below the emission bandwidth, now it can't do an up conversion, it can do only low conversion. So how the spectrum, emission spectrum is going to look like?
So you're saying to excite
Below the
energy
emission.
below the emission band?
No, below the emission bandwidth curve. So you have the emission bandwidth say from 650 to 700. So if I exit at 675, 675 in between there, so what will be my output? Will it have the lines below?
It won't create energy. Yeah, you'll always get emission at lower wavelengths.
So in that case, how the quantum yield is defined now? Is it going to change or?
No, it won't change.
Okay.
Yeah, the quantum yield is independent of, in almost all cases, it's independent of the excitation wavelength.
Okay.
Once you generate this state, once you get to this state, you get a quantum yield which is independent of how you got there.
Okay.
So once, the key thing about a triplet state that's important for the talk today is that, first of all, the triplet state is a long-lived state because it has a change in the spin of an electron. And so here the electrons are opposite spin because the opposite spin in the ground state, and they stay in opposite spin, but here now they become parallel spin. And once that happens, it now becomes a forbidden process to go from here to here because there's no way to change spin by phosphorescence. Photon does not carry spin. And so it's not that it becomes impossible, it just becomes forbidden. It's sort of like, your kids, things you forbid, it's not that they don't happen, they just happen a little less often, hopefully. But the point is that this state can be as long as a second, I say. So the key thing is that when you have something that goes into the triplet manifold, it's sensitive to much less frequent events. Because if the excited state is only lasting a nanosecond, then it's only sensitive to processes that occur within a nanosecond. Anything that are very slow, it's just going to be invisible to it because they don't happen often enough for that state to see it. But if the state lives a second, the events that are happening will be detected. And so the triple state is sensitive to very slow processes in the local environment. Whereas it may be just invisible to a short-lived state. And also a key thing about the triplet state is contact with oxygen is an instantaneous quencher. So oxygen will quench this state, but the key thing is it's not as high efficiency a quencher, but it's a very high efficiency quencher of the triplet state. And so the triplet state is actually very sensitive to oxygen and therefore can be used as a sensor for oxygen. And I'll show you some. But the final thing about the triplet manifold, and that's the important thing for today's talk, the most important thing, is that a large amount of research over the last 50 years has indicated that this transition, this non-radiated transition from the triplet state, is extraordinarily sensitive to local molecular motion in the matrix. So for example, if you put a triple state molecule in a liquid, it will be quenched very readily, but if you put it in a rigid solid, it will not be quenched. And so that's the first thing I want to talk about, is studying amorphous solids by using phosphorescent probes. And you familiar with amorphous solids, it's why we eat Weetabix and why we like crisps. So here what we're talking about is the triple state, and now what I'm interested in is using this rate of quenching non-radiatively as an indicator, as a surrogate for what's happening in the matrix. So if the probe is being used to detect what's happening in the matrix, we have to identify what process within the probe is being directly influenced. And like I said, a large amount of research has indicated that in a phosphorescent molecule, if we have the ability to measure this rate of non-radiated decay, what we really have is an indicator of how rapid molecular motions are occurring in the matrix. Because the magnitude of this number determines whether it can compete with how fast phosphorescence is occurring at a fixed rate given by the structure of the molecule, and if this process is occurring at a comparable rate, then you see a change in intensity. And if you have the ability to measure this, you can now assign a number to mobility within the matrix. And we can measure this fairly readily. If we measure the lifetime, the inverse lifetime is the sum of all three rates. If we eliminate oxygen by putting the sample in the presence of nitrogen, we get an inverse rate, the inverse lifetime. It's the sum of these two rates. If we put it in a very low temperature matrix, 77 K, we assume that this number is 0, and we can calculate this number. So if we know this number, and we eliminate this number, this measurement tells us exactly what K and R is, and by comparison of this lifetime with the lifetime of air, we can then, by difference, get this value. So we can easily calculate KQO2, the quenching rate for oxygen, and the non-radiated area. So let's look at it. Okay, so what we've done here in this experiment is we take riboflavin and about 1 part in 10,000. We mix it with a sugar and water. We spread it on a quart slide. We dry it extensively, as dry as we can, and we make it amorphous sugar. And then we measure the phosphorescence decay, and this is for riboflavin at 20 degrees in maltotetrose, and you see the decay is occurring on sort of the millisecond time scale. We fit the decay to a function which recognizes the fact that it's heterogeneous. This is a log versus time, so the curvature here is a measure of many, many different lifetimes. So it's not a single lifetime, it's a sum of a range of lifetimes. And this stretched exponential allows us to get at it. We fit up to a lifetime and a stretching exponent, and then we can calculate the average lifetime. And that's what we plot here. This is the average lifetime of riboflavin in a series of sugars from maltose, triose, etc., up to maltoheptose. So 2, 3, 4, 5, 6, 7. These are synthetic, so they're exact. And what I've done is I've plotted lifetime not versus temperature, but normalized to the TG. Because what I'm really interested in here is getting at a signal which will tell me what's happening either in the glassy or the rubbery state of this amorphous material. And what you see is that there's a very characteristic trend that at any given temperature below TG, as you go to a larger sugar, the lifetime goes down. Well, we're not really interested in lifetime per se. We're interested in this KNR value, so the rate constant. So we calculate the rate constant, as I mentioned on the earlier slide, just by comparison, and eliminating the oxygen and a measurement of the low temperature lifetime. Subtract that away, and now this is an Arrhenius plot of the log of the non-radiated decay versus a normalized inverse temperature. And again, we've normalized it to TG, so this is the TG right here. This is temperature below the TG, so this is all the glassy state. And what you see is this, non-Arrhenius behavior, curvature within the glassy state. And the key thing to note is as the sugar becomes more complex, the rate of matrix relaxation goes up. So the matrix is more mole, the more complicated it is. Well, that makes sense because you're making a glassy state out of the more complicated molecules. There's a lot more vocal motion occurrence, what we call beta relaxations within the glass. And those beta relaxations are actually interacting with the probe, quenching it. And so we've got a measure of how rapidly the matrix is moving to quench it. And this very clearly indicates that within this glassy state, you've got a considerable amount of dynamic heterogeneity occurring, and there's more dynamics the more complicated the matrix. The larger the molecule in which the matrix is made. Well, the key thing about this kind of a probe is, are we really monitoring what's happening in the matrix? Or are we just, monitoring what's happening in the probe? Is this probe just responding in some funny way to the matrix, or is it really accurately reflecting what's happening in the matrix? And one of the best ways to get at that question is to say, use a different kind of molecule with a different structure that will interact in a different way with the environment. So let's look at another molecule. Look at vanillin. Vanillin has a lifetime of a couple of 100 milliseconds in a nice rigid matrix. And if you put it in a similar sorts of environments, I would say starting with glucose to maltoheptose. This is a lifetime, again, T minus TG. You see the same sort of behavior. Glucose has a slightly different structure to the curve, but the rest of them are pretty much the same. And again, glucose at any T minus TG is much more rigid than the others. Do the same analysis, log KNR versus inverse TG, again, normalize the TG. Now I have to include values above the TG because KNR is still rising through the glass transition temperature into the melt. But again, you see essentially the same behavior. And that is that as you go to a more complicated sugar, the dynamics goes up. Question?
So what's TG? I just missed the point.
The glass transition temperature of the amorphous solid matrix.
Okay.
Yeah, so basically, with these sugars, when you dry them down, we take them from solution, we dry them onto a quart slide, and when you dry these sugars down, They do not crystallize, they actually just form an amorphous matrix. So it forms a glassy state rather than a crystalline state. So it's a glassy glucose. Of course, once we've heated it up above the TG, it will crystallize. In the experiment itself, it is an amorphous, it is a clear amorphous thin film of pure glucose.
One more question. So it's mix of lifetimes of non-radiative and the oxygen quenching and
No,
the
sorry.
phosphorus.
This is KNR. We have eliminated oxygen.
Yeah, okay.
Yes.
So can we use just a simple sugar as an oxygen sensor in this case? So if I do
No,
it
actually,
other way around.
for these probes can, in a sugar, do not provide a sensor for oxygen because the oxygen diffusion through the glassy sugar is not measurable. In other words, if we take like maltodextrose and we put it in an air environment and we put it in a nitrogen environment, you can't see the difference.
Okay.
The probe does not see oxygen. Oxygen does not diffuse through the matrix at a rate which influences the probe. I'm not saying that oxygen does not move through the matrix. I'm saying this probe does not see oxygen because again, it's got to be happening on the time scale. And oxygen has to collide with the probe on the time scale of the excited state. In this case, for having 200 milliseconds. I'll show you data from proteins, however, where the oxygen readily moves through the matrix on the time scale of the probe, and you can easily see oxygen diffusion, but not in these glassy sugars. Subtle differences. Whereas riboflavin is essentially completely quenched within the glass, the vanillin actually is not really completely quenched, at least in the smaller sugars, until you get into the milk. Again, let's look at another probe. This is erythrocin B. This is a red dye number 3. It has some iodines in it. It's intensely phosphorescent. We've used it extensively as a probe, both with proteins and with sugars. And again, you see essentially the same sort of behavior. As you go to higher sugar, you get higher mobility, and you get mobility both in the glass, especially with these higher sugars, but also within the milk. And so the key thing is that we've also seen this with tryptophan. I don't show you the data. So at least 4 radically different probes, different structured probes, are all really sensing. And so we think that this is a universal property of a probe within a sugar matrix we can measure. And the key thing is you can do these experiments in a microscope, so you can do it at a microscopic level. You can do it while the sugar is on a surface, not just, so you can essentially make a measurement of what's happening locally within a complex group. So I mentioned the oxygen, 1,000 or 10,000, I don't remember exactly, of erythrocin in that film. We spread it out, readily forms an amorphous protein glass. We make a measurement in the presence of nitrogen, pure nitrogen, or just air, that's oxygen. And again, you see now the influence of the oxygen. So you can analyze for what the quenching constant is, and that's what and you can also analyze for the KNR, and this is what how the KNR behaves. Now I do not normalize it because the glass transitions are, well, I'm not really sure what that means for these proteins. But we do see one that's different. It's hard to see any variation within gelatin, but of course gelatin is radically different. It doesn't really have the kind of structure. This is made so that gelatin is actually amorphous. It's not triple helical when you make these samples. The others are globular proteins, but you get the same sort of increase in dynamics as you start getting to higher temperature. But the key thing I'm showing this data is because I want to show you the oxygen permeability. So we analyze that, and we do this is an Arrhenius plot, again, with a quenching constant. And the key thing about the quenching constant is, does anybody trust Kleenex? I brought Kleenexes with me, but I left them in my pack. And now a napkin is just as good as a Kleenex. Thank you. And now I'm finding myself needing Kleenex. we analyze for KQ, and we do the Arrhenius plot, and we get what's fairly interesting behavior, which is that in all 5 of the proteins, beta-lactoglobulin, BSA, gelatin, lebanous globulin from soy, and alpha-lactalbumin, you get parallel curves, all giving an activation energy about 25 kilojoules per mole, which indicates that whatever dynamics are facilitating oxygen movement through the matrix is approximately the same in all the proteins. Question?
Are there any, I guess, specific rules or options when choosing these fluorophores for different?
Oh yeah, good. That's a great question. So our choice of fluorophores is based on what is known about the molecules that are either put into food or found in food. Okay. Chemists have been looking at natural products, the luminescent properties of natural products for 100+ years. And so there's a lot of reports, and that's how we choose them basically. Well, erythricin was the first one, based on the fact that it's a dye that has been used as a covalent probe. The modified erythricin has been used as a covalent probe in biophysics for about 40 years. And I use eosin, and I use erythricin as a postdoc. But the other molecules are based on just what is known about these molecules. And if there's for phosphorescent molecules, the key thing is that there's a report of a low temperature because prior to about 20 years ago, almost all phosphorescent studies were done at cryogenic temperatures. So if there was a report from a cryogenic experiment of phosphorescence detected in a naturally occurring molecule, we say, this is a potential probe for us. Because if it's phosphorescent in and the key thing is that people used to think it had to be the cryogenic temperature that was required for phosphorescence. No, it's not the cryogenic temperature, it is the rigidity of the matrix. So when you do a cryo experiment in spectroscopy, you're using like a glycerol water matrix that basically gives you a glass at 77 K. And that was the matrix for studying phosphorescence. But the key thing is it's the fact that it's glassy is the most important, rather than the fact that it's a 77 K to simplify things, but the key thing is that you have a glass, even at room temperature, you will get phosphorescence. And so that's how we choose, like, for example, these molecules. In the case of the other molecules, it's other sorts of reports. But basically, it's review of the current literature to say what molecules have a property, and they may say, oh, it's sensitive to pH. But, of course, it's not used in food, but it's been used as a pH sensor. Well, we say, well, it's a naturally occurring molecule, it could be a pH sensor. Does that help?
Yeah.
I think there is also an important point that is how well the probe molecules would mix with the matrix.
That's another key issue as well. And that's where the variety of molecules available is a help, because you have to not only, in terms of sort of making this match, there's a number of things to keep in mind. One is, can it sense the kind of property of erythricin, but then also can it disperse in and interact with the molecules of interest? So it's a fairly complicated, sort of landscape we're navigating here to find out. But so the key thing is these 5 different proteins, the similarity slope tells us something remarkable about what's happening in terms of what's allowing the oxygen to diffuse. But then the difference here becomes a little more complicated. But we think it basically, this slope is an enthalpy, is the enthalpy for whatever motion is allowing diffusion, but this is an entropy term. The fact that it's higher here than here with a similar slope means that these proteins have more ways the oxygen can diffuse through than these. In other words, it's really a difference in entropy available. But that's all I'll show you in terms of that. I just want to show you that now you've got the possibility of measuring oxygen. One that we're pretty excited about, but we're not clear how useful it will be is can you come up with a probe for water activity? We're looking at the flavanols. So there are lots of naturally occurring flavanols, and are found in the foods that we're supposed to eat. I'll show you data from 2 naturally occurring, but also from a synthetic one that's basically the core. Now, the key thing about flavanols is the following, and I'll have to start talking really fast now because we're running out of time. we're now looking at a different state. It's called an excited state intermolecular proton transfer state. And this state has properties different from this state, and I'll show you what they are. Well, the key thing about this state is the following, is that this molecule has the ability to undergo tautomerization. In other words, in the excited state, that proton can go over to the adjacent carbonyl and form the tautomer of this molecule. And the tautomer has lower energy. Sometimes doesn't emit at all, but in the case of the molecules that I'm focusing on, it has a lower energy and shifted from the regular emission, and so you see a double band emission when a tautomer forms, or single here or here. If it forms completely, you get one. If it forms just partially, you get two. If it doesn't form, you just get the one. And the important thing to note is whether this process occurs, it's not whether it occurs, it's how fast it occurs. Because basically, if it doesn't occur fast enough to occur before the molecule emits, you won't see it. But if it occurs fast enough to occur before the molecule emits, i.e. if the transfer occurs at a rate comparable to emission, then this state will form. But whether it forms depends on what the alternatives are. If there isn't any way for this molecule to form a hydrogen bond except with itself, then it will have a pre-existing hydrogen bond, and when you excite it, now the transfer can occur essentially instantaneously. If there's competition, then the transfer will occur slowly. So we can tell that there's competing hydrogen bonds. And so here's what we see. If you put it in a non-polar solvent, there's no competing hydrogen bonds. That means that there's an internal hydrogen bonded ring, which means the transfer occurs fast, and you only get emission from the T state. If you put it in a polar protein solvent, like methanol, glycerol, then whether you get it or not, depends just on local conditions, but you get some T and some N. And now the key thing is that maybe this difference, so let's put it into different water activity environments and see. Well, we did, and this is what you get, and you get both decreases in emission intensity but also shifts, and we did a lot of analyzing. It turns out it's not the ratio of the peaks that's sensitive. It turns out it's something we were a little surprised at. It's actually the Stokes shift that is sensitive to the local water activity. And the Stokes shift is the difference in energy between that peak and that peak. And if you plot the Stokes shift, the wavelength difference versus AW, this is in alcohol water. This particular one is ethanol, and we've done methanol as well. So in ethanol and methanol, we have a water activity probe. In this case of hydroxyflavone, we've got a probe which is essentially immune to the water activity up to about 0.7, and then it shifts. So this probe is sensitive to the water activity between about 0.7 and 1. Well, that's kind of a nice range. But it's not a natural, we can't eat that molecule. But we can eat 5-well, sort of. I mean, you know, you could potentially eat 5 that is naturally occurring flavidol found in foods. And we do the same thing, and Fisetin, we see now it's sensitive between about 0.82 and 1, which again is not a bad range. It's kind of appropriate range. So these two probes at least are sensitive to water activity in alcohol water solvents. Quercetin, no. Turns out we only see a single band. We're not sure what's going on. But quercetin is not sensitive. But at least in the case of alcohol water, unfortunately, however, if you use the standard way of monitoring or manipulating water activity, which is salt solutions, you don't get anything that really looks, so it's not clear. So it's like, this one may be a sense for water to be something else going on. So that's sort of a tantalizing program. The final one is not so tantalizing. It's pretty hard data. And now we've got, again, another singlet state, but now it's called a twisted intermolecular charge transfer state. And here's what's going on. So there are classes of molecules, and it's a fairly big class, as a matter of fact. It's now widely used in biophysics to measure things like viscosity in cells. There's molecules, and a lot of them we eat, which excite to what's called a locally excited state, and then they go to another state, which may be a TICT state or maybe another. But the key thing is, whether it goes into this state or not depends on the local viscosity, because this state involves some sort of change in the internal conformation of the molecule, probably twisting about some central set of bonds. And that twisting now, because it's a molecule that has, you know, a fairly substantial side chain, that twisting is sensitive to local viscosity. So if the viscosity is high, the twisting is slow, and you don't go into the other state. And the key thing is if you don't go into the other state, this other state, in case the molecules we're talking about, is completely dark. So if it goes into this state, you get quenching, complete quenching. And so if you see fluorescence intensity, it's because it didn't go into this state, which means that it was in a rigid or viscous environment. And so the intensity of the emission is sensitive to the rigidity of the environment. I'll show you the data. So here's what happens. So here's a purely synthetic one. This is kind of the gold standard molecular rotor, which is used in biophysics and adaptive cells, but it's not something you can eat. Here's a lower red, which is, at least in America, legal to put in food, and fast green, same thing. And these, they all have essentially the same behavior, which is that they have very little emission in fluid solution, but as you increase the viscosity of the solution, the emission goes up. Here's the way you plot it. Here's intensity versus viscosity. You see really steep curves. They're sensitive over the range of from say, up to maybe 10,000 millipascals seconds. You fit the curves by saying the intensity varies with viscosity as a power function, the viscosity, and the alpha, the power function, is a measure of how good, how sensitive it is to the viscosity. And here's our gold standard, it's 0.52, and these have values of 0.4. So these are actually pretty good molecular rotors. And so we look at them, and we look at them in a wide variety of viscous solutions, including hydrocolloid solutions, and although the hydrocolloid is a little bit more complicated. But then we want to say, well, these are synthetic molecules, and you know, if you go to the internet, these are molecules that will like kill you if you look at the label. So we, you know, people are working to get them taken out of food. So what about some molecules that may be a little bit more naturally friendly? And so here's anthocyanin. Anthocyanin also functions as a molecular rotor. Here's the data. Intensity versus viscosity. Betanin, which is the color found in red beets, yellow beets, it also increases in the same sort of fashion, perhaps others. So there appears to be a large class of both natural and synthetic molecules which are in or can be added to foods, which are also can function as what we call molecular rotors and be sensitive to local viscosity. Well, what about an application of that? So I've got a student who did a senior honors thesis and using fast screening to monitor assembly in gelatin. And we basically demonstrated that the probe is sensitive to the formation of local structure in a gelatin solution, but it's a little bit more complicated than we thought. So this is 0.1, 0.5, 1, 3, and 6% gelatin. These are not gels. These are gels. And yet the curves have essentially the same sort of structure with the fast phase and the slow phase. So the probe is sensing more than just some change in the solution viscosity. It may be actually binding to the gelatin framework. It may be binding to triple helices. We're sort of investigating. I'll take on some next year to continue this project. But more exciting is we now have molecules which are sensitive to local viscosity. So what about making measurements in unusual environments where we maybe don't have access to measurements normally? So we did some experiments in an in vitro gut system. This is a TIM1 system we have at Rutgers. And we basically wanted to measure what's happening in the part of the system, which is the stomach per se. So we use fast screen at about 40 micromolar, and we basically just put a fiber optic probe up against the compartment and make a direct measurement. And so the summary of the data is here. So this was part of a project to look at how oat influences the rate of digestion within a model system. So what we've done is collaborating with Mike Rogers from the University of Guelph when he was at Rutgers. We made simultaneous measurements of the intensity of the fast green as a function of time within the environment. And they pulled samples and made measurements of the total sugars. And so what we find is that there's a decrease in viscosity because the intensity decreases as a function of time. That correlates with an increase in the digestion of the carbohydrate in this oat matrix. And so what we've got is, at least in principle, the ability to make a physical measurement that correlates with some chemical change within the gut environment. And what's exciting about this is that with these probes, we can make measurements, at least in principle, within living organisms now. So in 2015, somebody generated a little device which is about 16 millimeters in diameter and 45 millimeters long. So if Yuri was feeling ambitious, he could actually swallow one of these. It's a wireless fluorescence spectrometer that you could actually swallow, and it could make measurements in your gut and then through your system, and then you just read out the data right through the radio. Or perhaps maybe you put it in a cow or a sheep or some other animal. But now, with this measurement, you could then simultaneously feed some appropriate probe to the animal and then make measurements within the gut, and it wouldn't have to be restricted to the measurement of the size. It could be some other probe which you may find that would be sensitive to some other property within the gut, and you can actually make direct measurements of what's happening inside the living organism as a function of digestion during feeding. So basically I've talked about 3 different kinds of probes. Triple stage, which can monitor mobility in amorphous solids. TIC, T-stage molecular rotors, which can measure viscosity in liquids. And then hydrogen bonding state, IPT states, which are sensitive to hydrogen bonding, may provide signals about water activity. The key thing is, this is just the tip of the iceberg in my opinion. There's other kinds of molecules which are in the foods we eat that we could use to measure other properties. And so what we have here is the potential of now applying photophysical techniques to measure what's happening in edible molecules. Is we could actually design into a food that we fabricate the potential for monitoring in that food at point of manufacture or at point of sale in a supermarket, what's happening within that food, just using one of these. Because everything I showed you in terms of a measurement can be done with a cell phone. Not at the high accuracy that I showed you the data, but in terms of making measurements of emission or lifetime can be done with a cell phone. So this I think has a lot of potential, and I want to thank everybody that actually did the work and paid for it. Dr. Maria Cordini, University of Guelph, did an enormous amount to keep things going, and then so to help graduate students, but also undergraduates, because a lot of these projects were done with undergraduate students because it's a great set of projects to have them done by tomorrow. So thanks. Not too much.
Thank you, Rick. Now we can have a few questions, please. I think there's a lot of interesting points. Maybe we don't have all background in the physics enough, but
yeah,
some questions may be welcome.
Yeah.
In your presentation, you showed experiments with sugars and proteins. Have you done any exploration into fats?
No, we have not. Well, not that I showed you. We have done some experiments. We got a USDA grant, and one of the aspects of the grant was to look at perhaps finding some molecules that could be useful in liquid oils to monitor some quality parameters, but didn't really find. I think we did actually publish one paper. At least one of the molecular rotors is a lipid-soluble molecular rotor, so we actually look at measurements of intensity in a crystallizing fat system. So yeah, so we've done a little bit of work, but not a lot of work. But that's just because money and people.
Okay.
There are a large number of fat-soluble molecules which you could look at that could provide. When I say the tip of the iceberg, the tip of the iceberg isn't it say 1/7? No, I think it's much. I mean, what I haven't talked about is like 98% of what's available. I mean, the point is that there's, each of these molecules has its own particular kind of photophysics, and there are an enormous number of potential edible luminescent molecules out there. I mean, like literally in the thousands. And sometimes, you know, it's whether there's a hydroxyl group on the ring system that makes a difference, and so, or where it is. You know, like quercetin versus fisetin, very similar. I mean, to a non-organic chemist, they're one of those, you know, they're the same molecule, because you just shift it around hydroxyls, but one is sensitive and one is not. So there's an enormous amount of work, retail work that needs to be done to sort of identify. And the key thing is to sort of buy into the potential of it. Then it's just a lot of hard slogging to look at, see what could be useful, and look at in the food system. And there's an enormous amount of data out there of the properties of these molecules, but none of it is directed toward what could be monitored in food.
Yeah, I was also going to ask about the fat soluble, because
Yeah.
there is a lot of fat soluble photoactive molecules that are not sold in food.
Yes.
But you mentioned oxygen many times,
Yeah.
and then you kind of showed the
Yeah.
bag of potato chips as well. So is there any way to monitor oxidation using these techniques?
No, I don't know. I can't say yes and I can't say no. But yeah, that's an issue that we've been, you know, hoping that we'd stumble on, is whether we can find something that could be sensitive. My gut feeling is yes, there's probably a way of getting at that, but we haven't really focused on it.
And then finally, just in layman words, if I have my phone and I had certain application, so what would be the thing I would look at the supermarket?
Basically, what you probably have is an attachment, because the phone itself, you know, I mean, it's got a light on it, but it's just a white light. You need probably an array of LEDs to give you different excitation bands, and you know, so that there'll be like it might be like an attachment with a set of LEDs on it, and then a grating that would fit over the phone. I mean, in terms of a detector, I mean, these things have revolutionized, for example, microscopy. I mean, modern microscopy is not done with this instrument at all. It's done with a camera. And the reason that you know, we can do single molecule fluorescence measurements routinely now is because there's been so much work developing the high quality sensors. So, I mean, this is the best camera I have ever owned. And I didn't buy a camera, I bought a phone. So it's extraordinarily sensitive. So you put a diffraction grating over the top, and now whatever is hitting that gets diffracted out, and all you need now is the software to interpret that diffraction grating in some particular way. So that's for like looking at emission color. In terms of measuring like a lifetime, then you have to have like an excitation source that's pulsed. And again, that can be an attachment, and then, you know, synced with the, whether it's, you know, it's just, you know.
That's in simple words. If I buy your food or not.
Oh.
What is the decision?
Oh, yeah. Well, no, I think it's no, don't buy that. That's on the tail end of the maturity cycle. I think with respect to fruit, I think you're talking about maybe, you know, taking some hyperspectral image and then saying, no, that's not getting right. It's past ripeness. Yeah. It's like this has got 3 days, not 10 days.
Okay.
You can eat it. I think that's potential. Yeah. Or, for example, it's a little bit more complicated. It's like a little clear panel on the thing, and it's not the consumer doing it. It's the the high school kid who's been taught how to use the app, who's just going around saying good, bad, and it's not used by data anymore. We're actually saying that you built into the food product a chemical whose signal will change at a definable point, where now the actual food on the shelf is bad rather than is it within or not being used by data.
So, but if you have these applications in every phone and you go to the supermarket and everyone's picking.
Well, maybe not every phone. Maybe it's just, I don't care what happens to it. I just want to.
Right, I know.
I'm not making bombs here. I'm making sensors. So.
Okay. Thank you. What question?
Oh.
So it's nice that you are focusing more on the fluorophores that are acquired naturally, so that it can be used everywhere. But the key is, what I would like to know is, what are the challenges that you would see in getting this natural fluorophore with respect to the artificial probes? So there are a lot of artificial probes, maybe different
well,
chemical.
from my perspective, it makes no difference. If it's a fluorescent molecule in the food, I can use it. I mean, it's just what other people have to say about the synthetic molecules. You know, like I showed you, we do a lot of work on the azo dyes, and of course, a lot of people of the world thinks that azo dyes will kill you, so they're trying to get rid of them in food, and people are starting.
Sure. Like, is it like, means there are some advantage of natural dyes, I mean, in terms of photophysics itself?
Oh, in terms of what I talked about today, natural and
intensity.
artificial makes no difference. It actually makes no difference whatsoever.
You have the same intensity.
You'll have
the same.
you know, same or different. It makes no difference whatsoever. The photophysics is completely independent of synthetic versus natural. In other words, it's a distinction that makes no difference with respect to the photophysics. Now, that being said, a lot of synthetic molecules, as you know, have been used because they're more stable. Okay? But with respect to some of the things I'm talking about, stability is actually sometimes a problem. Because it may well be that it's the fact that it's not stable that is the signal. You know, like for example, riboflavin is not very stable. It oxidizes very readily, it photooxidizes. So maybe that's the signal. And that's what we were actually, you know, did some work looking at, whether that's the signal. Loss of fluorescence tells you.
In terms of detection challenges, you have equal intensity of
it's all
one and the same.
Some of these naturally occurring molecules have a high quantum yield, some have a low
high
quantum
quantum
yield.
yield.
Yeah.
Okay.
Great, thank you.
Thank you very much. Now, there are sandwiches outside.